questions will be in somewhat of a different order than the ones that you were presented with, just because it's a random set. But and apologies for this one because it was supposed to be a check all that apply, but it ended up presenting itself as a multiple choice question. So I guess as long as you got one of them, one of the correct answers, you're fine. But it says which statement is always true? The product of a whole number and an irrational number is irrational. The product of two rational numbers is rational. The product of two irrational numbers is irrational. The sum of a rational number and an irrational number is irrational. All right, so a lot of words there, but it boils down to whether or not you know the definitions of whole numbers, irrational numbers, and so on. All right, so you start off with something, I guess, basic, like, okay, well, what's a whole number? So a whole number is a set of numbers that start with the number 0 and increase to infinity, excluding any decimals, fractions, or radicals along the way, all right, or at least non-perfect square radicals. Irrational numbers are the example, for example, anyway, something like radical 2, radical 3, radical 5, and so on. Just any radical that can't be simplified away. All right, so you wouldn't include radical 4, for example, in the set because radical 4 is equal to 2, and that's a rational number. All right, but any of these numbers can be put in the calculator, and you'll be presented with a decimal that never repeats and never ends. All right, although it may seem like it ends in a calculator, but it doesn't. All right. What it's asking us here is if I take any value from the first set and multiply by any value in the second set, will I always get an answer that has a radical that can't be simplified away? Well, the answer is no, because if I take, for example, 0 times radical 2, I would get a result of 0. And that's a whole number. It's a rational number. It's an integer. The one thing it isn't is an irrational number. So not irrational. All right, so that's not always true. So let's get rid of that one. The other one that's not always true would be the product of two irrational numbers. All right, that actually comes up again in the free response. So if I take, for example, I'll keep working with the radical 2. Radical 2 times radical 2. Radical 2 times radical 2 is radical 4. Radical 4 is 2. 2 is not irrational. Let me get the arrow in there too. Oh, it took off on me. Get in there. All right, there we are. All right, that's not irrational, so that's another one that doesn't work. But as it turns out, the other two do, and that's why this was a check all that applies situation, or it should have been anyway. All right, so no matter how much you try, you'll never be able to come up with a product of two rational numbers that is not rational. All right. A way of handling that, I mean, it's not ideal, it's not pretty, but you could do it on Desmos by multiplying some value A by some value B. All right. Create some sliders and just see what the result would be for particular rational numbers. So let's say I put in 1 times, I don't know, 3/2. 1 times 3/2 gives you 3/2, which is rational. All right, I turned on the little fraction tool there to show, I'm just going to move this down, to show that it can be expressed as a ratio. And then just move my slider and see if I'm still getting numbers that could be expressed as ratios. And it appears to be the case. All right, so that's one way to handle it. The other way is to just think, but sometimes our thoughts betray us when we're taking a test. It's the case where you try a problem 100 times 99 times you get it right. The one time you get it wrong is the time that you're trying it on a test, you know. So you just got to be careful. It's easy to say be careful, but you know, it is what it is. All right, so moving on to number 2. I'm actually going to move number 2 up to number 1 so I don't have to scroll too much. Cut and paste. All right, this one says the set of natural numbers is not closed under, you know, different operations. So closure, again, is the idea that you can perform an operation using a given set of values and the result will still be in the set of values. Right? So we worked with that a fair amount. The set of natural numbers, 1, 2, 3, 4, and so on, excluding fractions, decimals, and so on. All right, if I multiply any two numbers, add any two numbers, and you know, we'll get values that are natural numbers. The one instance where it won't be closed is if I divide. So for example, 2 divided by, I'll say 5, is 2/5. All right, that's not a natural number. That's not natural. All right, but if I take any two natural numbers and add them together, I'll get a result that's natural. Same thing with multiplication. All right, now I know some of us do not like Desmos, like absolutely hate it. And then there's some people that are like, oh, I don't mind it. I'm not going to do what you're doing with it, but I don't mind it. You can create the set of natural numbers. You can create whatever set that you want using Desmos. You just have to adjust your sliders. So if I look at, so I want to add two natural numbers. So what I'll do is I'll tap on this little lower bound here. That gives me an interval. It gives me an interval that I can work with. So natural numbers start with the number 1. So I would type in a 1. They max out at the number infinity, but I don't want to put an infinity in there, so I'll put a 20. And they're whole number values, so I would put a step value of 1. So let me just show you what that looks like. You see, it's kind of hard to tell, but there's little white dots in that gray bar. That's where the slider is going to land. It's going to skip over everything except for those little white dots. So if I slide along, it's only going to bring me to natural numbers, starting with the number 1. All right, I would do the same thing with B. So my slider B, starting it at 1, going to whatever I want. I'll go to 20 again with a step of 1. So again, now it's only going to give me natural numbers. So what I could do here is create the operation A times B. That's for the multiplication, A plus B. That's for the addition. And then now it's just, I could even do division. I've already evaluated that, but who's to say you know that going in? All right, so now I can look at it and say, all right, slide my slider, no matter where I put my slider, A times B always seems to be a natural number. A plus B always seems to be a natural number. A divided by B is the funny one. That's the one where it's like, well, that's not a natural number. All right, you could hit that little fraction icon to show what it'll become in simplest form, but it's definitely not a natural number. It's a fraction, right? It's a ratio or a rational number, right? So you could get it that way too. The benefit of Desmos, again, is you could save your work, and now that becomes a submission of work so you can get partial credit. My policy on multiple choice is I will give partial credit if you give me work. The regions won't give you partial credit. It's right or wrong, and that's it. For me, if you get it right, you get full credit. If you get it wrong, I'll still give you partial credit, but you got to give me work to give you partial credit. I can't read your mind. All right? I've been working on it, but I'm not there yet. So you got to give me some work, and what I will do on the test is I'm going to put a separate question in there that says upload or submit a Desmos link if you would like. You don't have to, but if you would like, submit a Desmos link. At the end of the test, you could submit handwritten work. All right? You're going to have to do some stuff on paper anyway. So you could, in addition to that, submit all the work for the multiple choice questions too. Hand that to me, and I'll use that to give you partial credit for the multiple choice. All right? For the Regents, again, you're on your own. I'm still hoping that the Regents won't happen. You know, there's no guarantee. I think it's going to happen, but you never know. But I'll give you partial credit.
So the test is on Schoology?
The test is going to be on Schoology, just like the practice test was, but there will be a component where you do it with pencil and paper.
Okay.
All right. So, for what values will the expression be undefined? Let me just, again, I'm just moving this up because I got the room, might as well, right? So, this question, this is actually, I mean, full disclosure, this is the reason why I'm doing the practice test. Because in the past, the majority of the students would get this question wrong on the first unit test. For whatever reason. I mean, maybe I didn't emphasize it enough when we were reviewing, whatever, but I'm emphasizing it now, I'll tell you that. All right? I don't want anybody getting this one wrong. This is something that everybody should be getting right. For what value or values of x will the expression be undefined? What you do is you take that denominator and you set it equal to 0. Then we're going to solve for x. All right? That little s in parentheses here, that means that there could be a single value, there could be multiple values. So you can't just dismiss it just because you see the s there. You can't just be like, well, it's not this or that. But, you know, it could be. You know, it's you gotta think it through. All right. Bottom line is solve the equation, add 36 to both sides. In case you're wondering, that's the addition po. They didn't ask us for that. It's multiple choice, but you got to be prepared for a free response question. I could ask you to justify with the property of equality. You got to make sure you do that. All right. X squared is equal to 36. I want to get rid of a power of 2. The way I handle that is by taking the square root of both sides. All right. And we talked about this in class. When you take the square root of a number, yeah, the square root of 36 is 6. But it's also something else. What's the something else? I'll give you a hint. It's written right there. Negative 6. So negative 6 or negative 6 will make this expression undefined. You'll see here, and this is a pet peeve of mine, the Regents folks, they're in love with the word and for some reason. And so this is actually a question that came right off an old Regents exam. There's absolutely no way a number can be both 6 and negative 6 at the same time. It's impossible. This really should say 6 or negative 6, but I have to write it the way the Regents folks write it, at least until the Regents is obsolete. But by Regents standards, this would be the correct answer. All right.
Will we definitely have to know this for the test?
Absolutely. Absolutely. Yeah, the only difference would be instead of a 36 on the bottom, it might be a 49. Yeah. But it's going to be same structure, same idea.
I'm like, this isn't exactly about the question. I'm just confused about something in general.
Okay.
Like, this is like, I like know what it is, but when I like ask questions about like rational and irrational numbers, I get like confused about like the repeating decimals and like which one is irrational and which one.
Okay, yeah, so when you're looking at a rational number, so when you're talking about decimal values, it's very easy to determine whether it represents rational or irrational. So if you have something like 2 divided by 3, you'll see the repetition there, right? The key is that what you started off with was a fraction. That fraction leads to a repeating decimal, and it always will. So if you had something like 1 divided by 12, repeating decimal, all right? Or, and if it doesn't end up being a repeating decimal, it'll be a decimal that ends, like 1 over 10. The irrational numbers are ones that can never be represented as a fraction. So a nifty trick when it comes to Desmos to determine if a number is irrational is to type it in. Let's say you have something like the square root of 16. If it gives you a clean answer, it's rational. If it doesn't, then it's irrational. And what I mean by clean is something that's either a whole number or something that can be represented as a fraction. So you see in this case here, in that little blue rectangle on the left, there's no little fraction icon. But let's say I have something like the square root of, I think it was 0.25. It came up later in the problem, but it's a radical. It looks like it would probably be irrational, but it gives you that little fraction icon on the left-hand side. That's telling you that it can be represented as a fraction, and if you tap on it, it'll give you the fraction answer. So we know just by that icon showing up that it's a rational number. All right. So that's really the key to everything, because if you put in something like the square root of 0.75, not too different from 0.25 under a radical, but this one doesn't have that little fraction icon next to it. This one does. This one doesn't. One's rational, the other's irrational. All right. And Desmos will really kind of save you when it comes to stuff like that. Let me just get rid of these pages, because I think, let me see. I'll skip ahead to the one that's relevant. Yeah, this one. For which value A of A and B is A times B an irrational number, it's really just a matter of typing it in and saying, all right, square root of 200 times the square root of 18 gave us a nice clean answer. That's rational. So 60, that's rational. Pi times 8. Oops. Pi times 8 gave us an ugly decimal. The decimal doesn't repeat. It never ends. And it also, the little Desmos trick, doesn't give us a little fraction icon on the left. So we know that this is irrational.
How do you get the fractions from the other side of it? Because mine isn't showing up.
It'll just show up if there is a fraction answer. So like in this case, when I type in, I'll just do it again. If I type in the square root of 200 times the square root of 18, it says the number 60. We're not worried about a fraction there because it's nice and clean. Right?
I didn't know if it would be like a whole number, like 5 or 1.
Oh, no. If it's just a whole number, it'll just leave it as a whole number. But when we do the 0.6 repeated times radical 0.25, that's where we'll see the difference. But this one is irrational. And that's because the decimal never repeats, never ends, and it doesn't give us that little icon. All right. Radical 5 times radical 5. That's a nice clean 5. That's rational. But then you get to this last one here. That's a little tricky when you have the repeating decimal. If you happen to know that 0.6 repeated is the same as 2/3, that's great. If not, what you do is you type in 0.66666, keep going, hit that little fraction icon, keep typing in the 0.6s, keep going until it converts it for you. All right. So it's kind of a weird Desmos trick, but right away you tap on the fraction icon, and this is only for repeating decimals. Tap on the fraction icon and keep putting in the 6s. Keep going. Then the fraction is going to disappear. You're going to think you're doing something wrong, but keep going. You got to get around 15 of them in there, 10 to 15, and then it'll make it a fraction again. And so now you know that you have the fractional equivalent. Then you can multiply that by the square root of 0.25, and you'll see it's a 1/3, which is rational. All right. So a question that came up in the other class was, is there a number that you can multiply pi by in order to make it rational? All right. So can you multiply pi by a number so that the result is rational? It's kind of a tricky situation, but the answer is yes. You could always multiply a number by its reciprocal and get a result of 1. That's what we call the multiplicative inverse. All right, that came up a couple of weeks ago. We spent all of like a minute on it. All right, so this is the multiplicative inverse. Which is really just the reciprocal of the given number. So if I have pi, I can write that as pi over 1. All right, any number you could put over a 1. 5, 5 over 1, 10, 10 over 1. If you multiply it by the reciprocal of that, so flip that number over, then you'll get a result of 1 in all cases. All right, so if I take pi and multiply it by 1 over pi, the result will be equal to 1. All right. So that came up because the student was trying to kind of look ahead and see if she could come up with any possible trick questions. I already made the test, so even if she gave me an idea, I'm not going to change the test, so it's fine. But she's thinking about a situation like, if a is equal to pi, and you want the result to be a rational number, what would you multiply by? That was the idea there. All right, it's kind of a fun thought process. I'm going to move another question down, or I'll move this one up. If you're still copying, just sit tight for a sec. Just trying to put it all together a little bit. All right. All right, the next one, the number negative 49, or 45 over 9, I should say, because that's correct, can be classified as what? Well, it's definitely real. If you don't remember what a real number is, just think it's not imaginary. Imaginary is negative under a radical. So if I have a radical with a minus sign underneath it, so like radical negative 3, radical negative whatever, doesn't matter. That's imaginary. That's not real. Everything else is real. All right. So if it doesn't have a radical in it, it's not going to be imaginary and it's not going to be irrational. So I'm not worried about those. All right. If it has a negative sign in it, it can't be natural because the natural numbers start off with the number, we talked about this earlier, start off with the number 1 and increase to infinity. 1, 2, 3, 4, 5, all the way up to infinity. Right? No negatives. The only values that involve, or the sets that involve negatives would be integers and rational numbers. Right? So negative 45 divided by 9 actually happens to be an integer because 45 over 9 is a whole number, 5, so tack on a negative here. We're looking at something that's an integer. It can be expressed as a ratio. And we already know it's real because it doesn't have a radical in it with a negative under that radical. So this has to be our final answer. All right, so that's a nice one, little process of elimination based off of knowledge of definitions. All right, but the key is you got to know the definitions. All right, I say it's a nice one, but it's contingent on whether or not you know the definitions. If you don't know the definitions, it's not very nice at all. All right, same idea with the next one. Which property? Well, if I wanted to simplify the left-hand side, I would distribute the 7 to each term. I'd multiply the 7 by the x and by the 3. Each one of those terms gets the 7. That's distributing, right? AKA distributive property. Commutative property is when you change the order. You're adding and you change the order. Associative property is when you're moving parentheses around. right? Whether it's addition or multiplication, that's not happening here. So you could also have gotten it by process of elimination. All right, I think I'm going to come back to this in a second. Yeah, there was another one, so let me just grab this. And I'll put it here. Gonna have to do some shrinky dinkies here. All right, there we are. Which equation is an example of the associative property of multiplication? So just a little reminder, associative property deals with just moving parentheses. You don't move anything else. So all the numbers, the variables stay in the same place, the parentheses move. However, this is even easier than that because this says associative property of multiplication. There's only one choice that actually involves strictly multiplication. Everything else has addition in it somewhere. So that would have to be the first choice here. But you could also see on the left side and on the right side, it's X, Y, Z in that order. The only thing that moved from the left side of the equation to the right side of the equation were the parentheses, or the only things that moved. All right, so that one's pretty not bad. Let me just get rid of these. And so the last little set of questions, one of them we've kind of already tackled, but we'll do it again anyway. Number 8, before we get to the one that we've already done. 11 times 4 minus 6x plus 5 times 13x plus 1 is equal to 9. We want to solve this using the distributive property, at least to start. So we're looking at 44 minus 66x plus 65x plus 5 is equal to 9. All right. It's algebra, so it's kind of prone to making little careless errors, so you just got to be careful. One thing that I did notice, and this is not in the territory of careless error, this is in the territory of glaring conceptual error, so we got to work on this, is that you cannot do what I'm about to do. All right? Do not do this. This is absolutely incorrect, and I'll explain why in a second. All right? I saw people doing this. I'm going to add 66 to both sides. All right. And they say, oh, I'll cancel this out, and I'll get 131x over here. All right? That is not correct, and the reason why it's not correct is that is a property of equality. Properties of equality are operations that happen to both sides of an equation. The purpose of a property of equality is to balance an equation. If I add something to one side of an equation, I have to add it to the other in order to keep it balanced. It's like a scale. All right, I'm adding 66x to one side. To keep it balanced, I have to add 66x to the other side. All right, that's the whole point. If you add 66x to the same, here's the equal sign. You add 66x twice to the same side of the equation, you just did this. All right, it's really, really imbalanced now. In order to balance it out, I'd have to add 132x to the other side. All right, so that's no good. We don't want to do that. Instead, what we want to do is combine our like terms. All right, we have two terms here that each involve an x. Put them together. Negative 66 plus 65, negative 1, negative 1x. 44 plus 5, 49. Whole thing is equal to 9. Now we can get our properties of equality involved. Subtract the 49 from both sides. So negative x is equal to negative 40. Then I'm going to divide both sides by a negative 1. And I'll get x is equal to 40. Now, just in case, we do want to be prepared to justify steps with properties. So in this case, I would have the subtraction property of equality. Abbreviations are fine. in a test, we want to do things a little quicker, so I'm not looking for an essay for each question. Reasonable abbreviations are okay. And division property of equality. All right, so just quick justifications. Number 9, 1/5 of a number decreased by 18 is equal to 2 times the sum of the number and 9. Write and solve an equation to find the number. All right, it's a word problem. As lame as it seems, we need a let statement. And as lamer as it seems, that let statement is let x equal a number. All right. It's definitely better on a practice test to see, oh, you needed a let statement here with no point deduction than it would be on a test to see you needed a let statement here minus 1. All right. So that was kind of like your little reminder. 1/5 of a number, so 1/5 x. Decreased means subtraction, so decreased by 18 is equal to, it just flat out said it there, 2 times the sum of the number and 9. So that's telling us to take the sum of the number and 9 and multiply that by 2, right? So that's telling us parentheses. Now, once you have the equation, it says solve it. It didn't say solve it algebraically. Solve it any way you want. Use Desmos if you want. I'll do it algebraically just so you have it, but I mentioned this when we were talking about word problems the first time. The big challenge is coming up with the equation. That's really what I'm testing here. I'd also like the solution, but I'm not looking for an algebraic solution. I got you with the algebra right here. I just tested you on the algebra. I don't need to test you again. All right, if you want to do it algebraically, that's up to you, but if you want to do it on Desmos, that's fine also. All right, so I'm going to multiply by 2 using the distributive property, 2x plus 18. I'm going to subtract the 1/5 x from both sides. Simultaneously, I'm going to subtract an 18 from both sides. They're both under the same po, so we're good. They're both subtraction po. All right, so I would just need 2 minus a fifth. Not afraid of fractions anymore with Desmos. 2 minus a fifth, just type it in. 1/8, geez. 1.8 x is equal to negative 36. If you don't like that, just put it as a fraction. Tap on that fraction icon. 9/5, I think I like the 1.8 better. Divide by the 1.8. That's a division po. And so we get x is equal to negative 36 divided by 1.8, negative 20. Word problems are presented in word form. The answers need to be presented in word form. As lame as it seems, the number is negative 20. I mean, that's for full credit. So we got to be careful. It's not going to feel good if you lose points for that. So you definitely want to make sure you take the time to do it. All right. And that's the kind of thing where, hopefully, this hardly ever happens, but you can't come to me at the end. You get your test back. Oh, could I have a point back for this? I didn't know I needed to write a let statement. I didn't know I needed to put an answer in word form. 1, the rest of the class is going to be like, he said it like 5 times. And 2, I have a recording. It's right here. It's going on YouTube. The whole world knows that these are the instructions. All right, so make sure you take this into account. The last one we already did, the closure. Irrational numbers closed under multiplication very quickly and easily. It's no because, for example, any example that justifies it is fine. Radical 5 times radical 5 is equal to 5, and 5 is not rational. Irrational. All right, these two numbers are each irrational. So we're starting off with the irrational set, and we're getting a result that's not irrational, so it can't be a closed set. All right. So